So we're in section 11.3. So the dot product is just one form of vector multiplication. And the dot product will turn out to be interesting and useful for various things that we're interested in doing. So let's define the dot product. I'm going to define the dot product if V is V1, V2. Oops, I don't need it. And U is, why don't I just we'll start with a three-dimensional vector, V1, V2, V3. And U is U1, U2, U3. We're going to define V dot U as V1, U1 plus V2, U2 plus V3, U3. And if we have a vector in the plane, then we just have one less component here, and we have one less term here. The other ways you'll hear this referred to, the dot product, it's also called the scalar product. Or the inner product. So both of those are just other ways of referring to the dot product. The inner product, I think, is a little older term. One important thing to remember, and every year people forget this, especially on the test, the dot product is a scalar. It's not a vector. So we're adding up the components here. So our dot product always gives us a scalar. A couple of properties of the dot product that are going to be important. So some properties of the dot product. U dot V equals V dot U. U dot V plus W equals U dot V plus U dot W. So we have the associative property. I'm sorry, the distributive property. And this first one is our commutative property. If we're multiplying by a scalar, C times U dot V is C times U dot V, and that also equals U dot C times V, and C here is a scalar. Zero depth vector dot product with any vector is 0. And this last one is important. W dot W is the magnitude of W squared. So these are properties of the dot product that we're going to that will be useful when we're trying to figure things out using the dot product. So any questions on this? So yes.
So normal zero dot into the
So you're saying a zero scalar?
yeah, zero scalar.
This is not a proper operation because we have to take the dot product of two vectors. So this first one would have to be the zero vector.
No, if zero is a constant.
Then if this
Up there you get zero.
right, so if we had a scalar, if we had 0 times v, then
That's what I meant.
okay, that would be the zero vector, yes. All right, let's talk about dot product and angles, because often we're talking about vectors and their angles between them. So if I have two vectors here, like so, and this is u and this is v, and this is the angle between them, theta. If we have 0 less than or equal to theta less than or equal to pi, then we have that the cosine of theta is u dot v over the length of u times the length of v. So this is a way, using the dot product, we can determine the angle between our vectors. So we could also rewrite this and say that u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. So this particular representation of the dot product turns out to be very useful when we know something about the vectors and angle between the vectors, between those vectors. We can also use this representation to figure out the angle. If we're interested in the angle between the vectors, we can use this representation to figure out the angle. Anybody have an idea of how we come up with this? What's that? Did someone say triangle? Triangle? Is that what you said?
Oh, is it based
Yeah.
on law of cosines?
It's based on the law of cosines. Eric said law of cosines, but he's looking in the book. So this comes from the law of cosine. So let's look at the proof, because I think this is a nice illustration of how we use the properties of vectors and the properties of the dot product to actually come up with a result. It's a short proof, so we're going to use the law of cosines. So here I'm going to redraw this figure. Here's my figure, and I'm going to draw this vector here in red. So this is u, this is v, this is theta, and the red vector is u minus v. So let's use the law of cosines on this triangle. So the magnitude of u minus v equals the magnitude of u squared plus the magnitude of v squared minus 2 times u. Yes, this should be squared. Thank you. U, magnitude of u, magnitude of v, cosine theta. Now, one of our properties of the dot product was that u minus v, magnitude of that squared, is u minus v dot u minus v. And now I can use the distributive property for the dot product and say this equals u dot u minus u dot v minus v dot u plus v dot v. Which equals the magnitude of u squared minus 2u dot v plus the magnitude of v squared. And then now I'm going to substitute this expression in, so I get u squared, magnitude of u squared, minus 2 u dot v plus the magnitude of v squared equals magnitude of u squared plus the magnitude of v squared minus 2 u dot v cosine theta, or sorry, magnitude of u, magnitude of v, cosine theta. My arrow didn't turn out right. There we go. And then I can rearrange this and say u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between. Pretty nifty, huh? So this property that we just talked about comes from the law of cosines. Now tomorrow I have a really cool thing. I'll show it to you briefly at the beginning of class. That comes from this. It's a really when I first saw it I was like that's such a cool thing. So we'll talk about that tomorrow. So questions on this. The important thing from this is to realize that we have this relationship, and using the dot product we can figure out the angle between two vectors. All right, one consequence of this is that the magnitude of u times the magnitude of v is always greater than 0. So depending on the sign of the dot product, I can figure some things out about the angle between them. So let me draw a few pictures here. So if we have these different arrangements of our vectors, if the angle is acute, u dot v is greater than 0. Our cosine is positive, and the magnitude of u and the magnitude of v are always positive. So if we have an acute angle, the dot product is greater than 0. If we have an obtuse angle, u dot v is going to be negative. It's going to be less than 0. And if we have a right angle, u dot v is going to equal 0. So if our dot product is 0, that tells us our vectors are perpendicular to each other. So we can look at the sign of the dot product and figure out something about the angles. Now, one quick thing about notation, or terminology, I guess. we use the word, if we're talking about a 90-degree angle, a right angle, we use orthogonal, the word orthogonal, to refer to vectors. So rather than saying vectors are perpendicular, we normally say vectors are orthogonal. That means they intersect at a 90-degree angle. It's not incorrect to say that they're perpendicular, but just kind of common usage, we say vectors are orthogonal. We talk about perpendicular. Perpendicular usually refers to lines and planes. So we would say lines are perpendicular to each other, planes are perpendicular to each other. And normal, we talk about normal, when we refer to vectors in relation to lines and planes. So we'd say two lines are perpendicular, two planes are perpendicular, a line is perpendicular to a plane. We would say a vector is normal to a plane. And normal vectors are going to play, we'll work a lot with normal vectors next semester. But just wanted you to be familiar with the different ways of referring to the different things. Like I said, it's not incorrect to say the vector is perpendicular to the plane. It's just common usage. We would say the vector is normal to the plane. The vectors are orthogonal to each other. All right. Do we need to see an example of calculating a dot product and figuring out the angle between two vectors?
Do an angle one.
An angle one. Okay. So let's look at u. Let's say u equals I minus 2j plus 2k, and v equals minus 3i plus 6j plus 2k. And we want to find the angle between u and v. So we're going to say that the cosine of the angle, using the relationship that we talked about, is u dot v over the magnitude of u times the magnitude of v. So that would be the dot product. We get minus 3 minus 12 plus 4 over the magnitude of u is the square root of 1 plus 4 plus 4 times the square root of the magnitude of v is 9 plus 36 plus 4. So we end up with minus 11 over the 3, this turns out to be 3 times 7. So we get minus 11 21st. And theta would be the inverse cosine of minus 11 21st, which turns out to be about 121.6 degrees. So our dot product, our dot product ended up being negative, so our angle is obtuse. And that's all there is to find an angle between two vectors. It depends on the question and the application. You can do it in degrees or in radians. This one turns out to be about 2.12 radians. And if the cosine turns out to be 0, then you know that the vectors are orthogonal. And if the cosine turns out to be -1, you know that the vectors are oppositely opposed, so they're situated opposite. So the angle between them would be pi over 2 or 180 times pi or 180 degrees. Questions? All right, so one way that we use vectors, or dot products, one way we use a dot product, we're often interested in the projection of one vector onto another. So that's what we're going to talk about. The last thing we're going to talk about is vector projections. So an example of when we would want to be, when we want to look at vector projections would be if we're talking about force, vector force. And we want to know the force in the direction, say in the direction of motion. So we want the component of the force in the direction that you're moving. Or if you're in physics, you're talking about inclined planes, you want the component of the force that's parallel to the plane, and you want the component of the force that is normal to the plane. So you're breaking down your vector force into different components in different directions. So that's one instance where we would want to find out the projection of one vector in a certain direction. So what we're interested in is if we have a vector u. What we want to do is break this into two components. And we're going to call the component here we're going to call this component W1. So this is, I'm just extending this out a little bit, making this into a vector. So this is vector W1, and this is vector W2, and this is vector U. So what we want, we write that U is W1 plus W2. So we want to figure out these components that add up to the vector U. And we want W, and this is vector U, this is vector, the red vector down here is vector V. So we want these components in the direction of vector V. W1 is in the direction of vector V, and W2 is orthogonal to vector V. So we want the components of U that are parallel to vector V and that are normal to vector V. So we want W1 is parallel to this vector V, and W2 is orthogonal to V. So we're interested in the components of U that are parallel to vector V and that are normal to vector V. So we give these, and I think this would be an example of where Eric said he likes the physics way of doing vectors more than the math way. So we give these some names that make what we're talking about seem more confusing than it really is. So W1 is called the projection of U onto V. So we're interested in vector quantities. We're interested in these are vectors that we're talking about. We call W1 the projection of U onto V. So we're finding this vector, the component of vector U that is parallel to vector V. So we call it the projection onto vector V. And we write this, the way you see it, is W1 equals the projection onto V of U. So this would be the terminology that you would see, the projection onto V of U, or the projection of U onto V. And W2 is called W2 is U minus W1, and this is the vector component of U orthogonal to V. So we can, W1 is this projection of U onto V, this vector projection, and W2 is U minus W1. That will give us this vector. And we call it the vector component of U orthogonal to V. And it's important to remember we're talking about vector quantities. We're not talking about the scalar projection. We're not talking about the magnitude. We're talking about a vector quantity. So how do we find these? Anybody have any idea what we might do here? What have we been talking about? The dot product. We use a dot product. So we're going to use the dot product. So I'm going to redraw this, and we're just going to look at this component W1. So we're going to use this diagram, but I'm just going to look at this component W1, and we'll figure out how we can determine this vector projection. So here's my vector. Here's U. Let me go back. I want that in black. And here's V. And I'm going to continue this out. So here's U, here's V, and here is W1. And if if theta is the angle between these two, this is theta, what is the length of vector W1? Magnitude of U times the cosine of theta. Well, what this magnitude of U cosine theta is part of what? It's part of the dot product. That equals U dot V over the length of V. So U cosine theta is U dot V over the length of V. This is a scalar quantity. This is a scalar quantity. We want a vector quantity in the direction of V. So what can I do with this scalar quantity to get a vector in the direction of v with this magnitude. Multiply it by a unit vector in the direction of v. So to get the vector quantity, I'm going to take this scalar magnitude, that's the length of this vector w1, and I'm going to multiply it by the unit vector in the direction of v. So the vector is going to be u dot v over the length of v times v over the length of v. That's our unit vector in the direction of vector v. And the way that you'll often see this written is u dot v over the length of v squared times v. And this is also, going back to here, this is the length of u times cosine theta times v over the length of v. This is our magnitude, and this is the vector, unit vector in the direction of v. So just to tie those two, the two representations together, we're going to say, and the way you'll see it in your math books, I don't think this projection, you might see it in physics, I don't ever remember using the projection terminology. We just thought about it as this quantity times a unit vector. But we say that the projection onto v of u equals u dot v over the length of v squared times v. Now, one reason that we would use, and this is the same again as u cosine theta, the magnitude of u times the angle between them, times v over the length of v. Now, one reason you would use this first representation, in this first representation you don't need to know the angle between the vectors. All you need to know is the component forms, and you can calculate this quantity. To use this quantity, you have to know the angle between the vectors.
Was that the magnitude of u out in front?
The magnitude of u, yes. I try to put the little tail on v to me. So in this first form, we don't need to know the angle between the vectors. In the second form, we do need to know the angle between the vectors. So that would be the difference. That would be why you would use one versus the other. And then to find W2, we just said that W2, the component that was orthogonal, is u minus W1. So if I draw my other vector in here for W2, I draw that up here, and we say that's W2. W2 is just u minus W1. We can figure out W1 from this, and then we can subtract to get W2. Questions on that? Do we want to see an example of calculating our vector projection? Let's do it. Let's do an example of calculating the vector projection. It's not complicated. Sometimes I think it's easy to get bogged down in the terminology of what's actually going on. If we remember, we're just looking at a component in the direction of a particular vector, and how we figure that out with our triangles. Like Garrett reminded us earlier, we're using triangles here. If we remember that, then we'll be fine. So let's say that B, I'm going to use A and B because I have my U's and B's tend to look the same. B is 2i plus j minus 3k, and A equals 3i minus j. So we want, in this particular example, we want to find the projection onto A of B. And we want to find the vector component of B orthogonal to A. So what we're saying here is that vector B is our two components, W1 plus W2, one that's parallel to A and one that is orthogonal to A. So W1, our component that's parallel to A, is the projection. I just want to use this terminology so it'll be a little more familiar when you see it. Projection of B onto A is B dot A over the length of A squared times A. So B dot A, let's calculate our quantities. B dot A is going to give us what? 6 minus 1 plus 0, so we get 5. The magnitude of A squared is going to give us 3 squared plus 1 squared. We get 10. So W1, plugging our quantities in there, is just going to be, this gives us 1/2 times A, which is 3I minus J. So we just get 3/2 I minus 1/2 J. So that would be the component, the vector component of B that's parallel to A. And W2 is B minus W1, which gives us 2I plus J minus 3K minus 3/2 I minus 1/2 J. All right, good. Okay, we're good. And this gives us, when we add this together, this gives us 1/2 I plus 3/2 J minus 3K. Those are our two vector components, one parallel to A and one orthogonal to A. We can check that W2 is orthogonal to A. If we take the dot product of this quantity, this vector, with vector A, we would see that we get 0. So if we take the dot product of W2 with A, we would get 0. And that tells us that the angle between them is 90 degrees. We can see that W1 is parallel to A because it's just A times 1/2. So it's a scalar multiple of vector A, so that tells us that it's parallel. That's a way that you can double check your work. You can form the dot product with W2 and the vector you're interested in. It needs to come out to 0. That'll guarantee you that it's orthogonal. And if we can look and see that W1 is a scalar multiple of A, so they're parallel. And if we wanted to double check, our third check is we could add W1 and W2, and we should end up with B, which in this case we do get. All right, questions on the dot product? Okay, I just wanted to tell you a little bit of history. In math class, Aristotle used vectors to describe forces. So vectors have been around for a long, long, long time. Descartes developed the idea of resolving vectors into components parallel to the coordinate axes. So he was interested in, Descartes was interested in the coordinate plane. So he worked with the idea of using the components like where we use our standard unit vectors. Descartes was interested in breaking vectors into components that are parallel to the axes. Vector algebra, which is really what we're doing, was developed by a gentleman by the name of Osiah Gibbs. He was a mathematical physicist at Yale. In the 1870s is when vector algebra was being developed. And an English mathematical physicist by the name of Oliver Heaviside. Heaviside is where the Heaviside cover-up method comes from for doing partial fractions. And this was, like I said, in the 1870s. And the ideas came from more theoretical work in the 1850s and 1860s by a gentleman by the name of William Hamilton, who was a mathematician, and Hermann Grossman, who interestingly was a linguist, a physicist, and a geometer. So vectors are a relatively recent, the idea isn't recent, but the stuff that we're doing with them is a relatively recent development mathematically. I can find those facts. All right, homework. The part we were all waiting for, right?
Yep.
Let's see, where are we? What day is it? It's Friday. 8th. Thank you. 787. There you go.